In this problem, we talk about something known as the rational roots theorem. This quantifies what rational numbers can actually be a solution to a polynomial equation. It says nothing about irrational numbers. So if you have roots that happen to be square roots and stuff like that, the rational roots theorem doesn't apply. But it does apply to rational roots that can be written as fractions. So we begin first by discussing it and then seeing how it works. So we first say let f be a polynomial. Polynomial in descending order, an x to the n, where n is some positive integer, all the way down to its lowest term, the constant term, a0. So we said let that be a polynomial. We then say the rational number, p over q, in lowest terms, so we're has to be in reduced terms, so reduce the fraction to lowest terms, is a 0 of f of x if and only if p is a factor, the numerator is a factor of the constant term a0, and q is a factor of an, the coefficient of the highest power. So it turns out we only have to look at those. And a lot of this, the reasoning behind this goes back to how you would factor a polynomial, to kind of see how that works, and we'll discuss that maybe a little more in class. But this is the rational roots theorem. It gives us a way of quantifying the potential rational roots. Okay, so now we're going to see this thing in action. So consider the polynomial 2x to the third plus 3x squared minus 23x minus 12. So we first recognize a sub n and a sub 0. We then look at the factors of a sub 0. So first, plus or minus 1. Right? Factors can be positive or negative numbers that would multiply to give you negative 12. And then we list all the factors of negative 12 out. Plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. We then look at the factors of a sub n. Fortunately for us, there's not too many of them. We then look at all the possibilities, taking every one of the guys from the list of a0, dividing them by every guy from the list of a sub n. So first, you take every one of those a sub 0s and divide it by plus or minus 1. That would give you plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Okay, then we take each one of those fractions and divide it by 2. So we get plus or minus 1/2. Now 2 over plus or minus 2 would be just 1. That's already in our list. 3 over 2 would give us 3/2. And then we would have 4 over 2, which would be 2. We already got that. 6 over 2 would be 3. We already have that. 12 over 2 would be 6. And we already have that. So this is our complete list of candidates. Now, that's not to say these were all zeros of that thing, because we know it's a third degree polynomial, so it's only going to have at most 3 of them. But we take this list now, and in the old days, you would have to do synthetic division on every one of them, or evaluate the polynomial at every one of those values to find out what works. Well, that's what we're going to do, but we'll leverage our table menu of our graphing calculators to do this much quicker. Give us a quick way to evaluate this thing a whole bunch of times. And so to find out which one works, we're going to just do that. We test each value for that function. If the function gives us 0, then we know that that number is a root of the polynomial. And then much like we did in a previous video, once we find a root, we can divide it out. And so you could take your function f of x, put it into your table menu, and then just start evaluating. 1, negative 1, 2, negative 1, 3, negative 1, until you find something that works. Well, I'm going to tell you that f of 3 works. So plug f of 3 in, and you get 0. And then I'm going to do synthetic division now to see what I get. So the 2 comes down. 3 times 2 is 6. 3 plus 6 is 9. 3 and 9 is 27. Negative 23 and 27 is 4. 3 and 4 is 12. 12 and 12 is 0. So that would mean that our new result, once we divide out x minus 3, is 2x squared plus 9x plus 4. Now, generally speaking, once you get it down to a second degree polynomial, we can go to the quadratic formula and find the rest of the answers. But I'm going to go a little further with this synthetic division, because I also know that f of negative 1/2 gives me 0 when I do the test. So I want to show you that this synthetic division also works for dividing out fractional terms. It still works the same way. So we take our 2, 9, and 4, because we don't need to deal with the original one now, just what's left. And we go through. Bring down the 2. 2 and negative 1/2 is a negative 1. 9 minus 1 is 8. Negative 1/2 and 8 is negative 4. We get a remainder of 0. So that means we're left with 2x plus 8. Well, we can set that equal to 0, that linear equation, and solve it very easily to get that x is negative 4. So giving us the 3 zeros of this polynomial, 3, negative 1/2, and negative 4. So this is an introduction to the rational roots theorem and how we can use it to reduce the degree of the polynomial down to something that's a little easier to solve.